equations. But really and truly, we're just going to be taking what we've already done and tweaking it just a little bit. So let's look at work. These are just some things dealing with work that we're going to be looking at in detail. This chapter and chapter 7. I'm not sure how much of chapter 7. Chapter 7 kind of expands a little bit on conservation of energy, so we will get more into the detail into that. But basically what we're going to be looking at, notice the key thing here, we're looking at the relationship of force done on a body. Okay, now you say, well, we've already been talking about that. Well, yes, we have, but we have not actually, we've looked at force, we've looked at Newton's second law of force and acceleration. Now we're looking at force on a body through a given distance, through displacement. Okay? So we're taking this then, and now we are looking at it being applied through a given displacement. Okay? Likewise, kinetic energy, energy of motion, okay, can be defined, we can define it a couple of ways. Work is actually, and I'm kind of getting a little ahead of myself, is equal to kinetic energy. Okay? So work and kinetic energy are basically, now listen closely, they are basically the same thing. And so is potential energy. However, potential energy is written this way. And we can put a delta there. Work is actually equal to negative potential energy. U is potential. And I'll explain when we get on into this, okay? All right. Okay. So let's dive into this. Are you ready? Okay. Okay. All right. So we've defined what kinetic energy is, the energy of motion. It's the energy. You don't have to write everything on the slide, just what I'm writing down. Energy of motion. Okay? And that is a form of work. Okay? Now, when we take kinetic energy, we take potential energy, we take work, and put them all together, then they become what? Conservation of energy. In other words, when we look at how all three combine, we're looking at how energy is conserved. And we will do, hopefully, a little later on, probably a couple of weeks, yeah, either next week or week after, we will look at conservation of energy. We will compare kinetic to potential. And basically, what is kinetic and potential? They're opposites of one another. For example, I hold the pen up, has very high potential energy, but zero kinetic until I release it. And as I release it, the kinetic energy does what? Becomes higher and higher, it increases, and what happens to potential? Lower and lower and lower until, boom, it hits the surface. Okay? Okay. All right. Okay, so let's define work. How do we define work? Work, anytime we apply a force to a body and it undergoes a displacement, delta X, then that is considered work. And so how do we define it? By definition and by mathematical definition, work is a force applied through, and this book uses S. We could use delta X. Now, why do they use S? S is displacement. Why do they use S? Well, work is actually a scalar quantity. Okay? So work is you better remember that, a scalar quantity. All right? In other words, it's the dot product. It's the dot product of the force times this displacement. So we use S instead of X. Now look, y'all, I am not going to get all heebie-jeebie-jeebie on this about if I use an X or an S, okay? Because some books will use an X, okay? We're not going to freak out over it. It's just displacement, all right? But it's the dot product, the scalar product, okay? So in other words, well, I thought displacement and forces are vectors. Well, they are. They are. So how in the world do we have work, a scalar quantity, when force is a vector quantity? All right. Listen closely. All right. We are not concerned with north, south, east, and west when it comes to work. Direction. All we are concerned with is the angle at which, listen closely, the angle at which the force is applied. Does that make sense? Well, a direction, angle is a direction. Well, yes, but remember, when we talk about vector products, remember direction actually means direction, like north, south, east, west. Okay? It really does. Okay? We're just concerned with work, okay? Did we apply the force horizontally, or did we apply it 25 degrees, 30 degrees, 45 degrees? Because that changes the value of the work, okay? Well, it could be up, okay? See, I could be going up and pushing at a 45-degree angle, all right? But again, we don't care about north, south, east, and west. All we care about is what angle was the work applied to the object. So it's the dot product, scalar product, okay? Now, and so our equation becomes what? We actually throw in cosine. We'll get to that in a minute. Let's look at the units. So the unit for work is named the joule, of course, after good old James Prescott Joule. Let's see, was it Joule that was born to a family of brewers? Yeah. And he was fortunate enough to have a lab to work in. He cared nothing about beer. Cared nothing about it. But he did enjoy using his family's wealth and their lab to do his work for work in. Yeah, he studied work and energy. Remember, I think I told y'all, maybe it was other class I told, that on his honeymoon, boy, this is some honeymoon, baby, I'm going to go out and measure the mechanical energy of work. See you later. He really did. While he was on his honeymoon in Switzerland, one of his early works, he was measuring the mechanical energy of work from measuring the change in temperature of water as it fell over a high waterfall there in Switzerland. I forget the name of the place. On his honeymoon. I'm like, dude, this is your honeymoon, okay? Let's leave experimentation at the lab, okay? Let's go on the honeymoon. But anyway, I reckon she really loved him because they stayed married. So anyway, I know what my wife would do. She would push me off the waterfall, Leave work at the house, Jack. All right, now, okay. Well, I'm serious. He really is on his honeymoon, all right? And, of course, his thermometers, the only problem with his experimentation there is his thermometers were not precise enough. But it did get the attention of the scientific community, and he later on refined his work there and defined the mechanical equivalent of work. And that is what? 4.186 joules is equal to what? 1 calorie. 1 calorie is 4.186, or 4,186 joules per kilogram. Okay? Now, so he defined the mechanical equivalent of work. Now, so again, this is the simple way. Now listen, again, how do we write it? Well, the unit again is a joule. What is a joule? It is a Newton meter. All right, now let's break this down, y'all. Please learn your units. If you don't get anything out of this class, I pray to God you at least know what a Newton is, a joule is, a watt is, and you know how to break them down, because that's important in engineering school, because I've had kids come back and tell me, Mr. Shields, make sure they know how to break their units down. All right, what is a Newton? A Newton is a kilogram meter per second squared. So what is a joule, actually? Well, we got a meter, so let's put those together. We've got a what? Kilogram meter squared per second squared. Right? Right? Because work is defined as the force times the distance, and I'm going to go ahead and give you this formula, and you're fixing to get it on a slide. Cosine of theta It's the direction of the force applied. Now please listen closely. It doesn't always have to be in that direction. What if I'm wanting to know about how much work gravity's doing? Well, which way is it? Well, it's the direction the force is applied. So now x goes that way. In other words, it'd be the cosine of that angle in that direction, which would be the cosine of 0, because again, it's the direction that the work is applied. Okay? So if gravity is pulling an object straight down, we're wanting to know how much work is applied, how much work by gravity is applied right here. Okay? Well, again, 0 being pulled straight down, isn't it? Okay?
Why is that not 270?
Because it's the direction that the force is being applied to the object. So in other words, the force is in this direction, so therefore it's also, your 0 degree is going to also be in this direction. Now, go ahead.
If it's pointing this way, force this way, it's 0 still.
Mm-hmm. Now it does get a little squirrely when we get on an incline, and I'll explain that when we get to that, okay?
Would it still be cosine doing like gravity?
Yes.
Going down? Okay.
Yeah, and that's where it gets a little confusing, and we'll get to that on a problem, okay? We'll get to that on a problem. So let's just kind of keep that in the back of our mind and remember, because when we get on an incline, then we have to look at 90 and everything, because typically, all right, for example, if an object's sitting on a surface like that, is there any work being done by gravity? It's not moving, is it? So there is work done by gravity, but would it be positive or negative? You see what I'm saying? See, if I'm pushing in this direction, the work done by gravity would be what? Would there be any work done by gravity? Because as you said, it's based on which direction the force is applied in. So I'm pushing it this way, but gravity's that way, isn't it? And straight down is what? Well, 270. What's the cosine of 270? 0. What would be the work done by the normal force? I'm pushing it in this direction. What would be the work done by the normal force? Well, the normal force is what? Straight up, isn't it? Well, what's straight up? 90. What's the cosine of 90? 0. So again, we got to look at the application and what is actually happening. Now, what if I'm climbing a ladder, though?
That's 270.
Okay. See, if I'm climbing a ladder, all right, if I'm going straight up or at an angle, then the work done by gravity is in the opposite direction, isn't it? You see what I'm saying? So in other words, if I'm climbing, now see, here's where we got to watch and listen to what we're saying. Now, I'm kind of getting a little ahead of myself, but since you mentioned it, I'm going to say it. All right, if I'm climbing up the stairs, who's doing the work? The gravity or me? You. So therefore, gravity is going to be what? Positive or negative? Negative, absolutely. But, all right, if something's dangling on a rope, it's just dangling there. Is gravity going to be positive or negative? It's not moving. It's going to have very high positive because it has the potential to do what? Okay? So again, how is the force applied, and what are we looking at? And so this is a little, it can get a little bit, you have to listen and draw it and look at how it's applied. Okay, back to the units now. And we'll look more into that, and that's why I want to try to get through all the lecture part, and then we're going to look at problems, because, again, how is it applied? Okay. So look, kilogram meter per second squared becomes a what? Joule. So I do want you to know that a kilogram meter squared per second squared is the same as a joule, which is the same as a Newton meter. You follow me? So if I were you, now again, if I were you, but you don't have to, on my card, on my formula card, units for joule, I would write a Newton meter, 1 joule, but I'd also write kilogram meter squared per second squared. Because when we do 1/2 mv squared, what is it going to be? Kilogram. We square velocity, it becomes what? Well, velocity is meters per second, and you square it, it becomes meters squared per second squared times kilogram. Becomes a joule. You follow me? Joule. Same thing. Same. All right. So, work. Here we go. That's what I wanted to get to. All right. This is, boy, you better underline this, for a constant force. Constant force. Constant force. What if it's a non-constant force? Well, we'll get to that. It becomes an integral. We have to integrate. Because you have to look at the, here we go, area under the curve of a graph. Now, when we use Logger Pro, it becomes easy. We just highlight the area under the curve and hit integrate. Or, if we have a function, we integrate the function. All right. But we're not to that yet. Constant force. All right, so here we go. So here's your work equation. That's for a constant force. Now, okay, we can compact it. Let's say that the direction, let's say, for example, if we are in the horizontal direction, what is that angle always going to be? You're moving this way, it's going to be what? 0. So we can just forget the cosine of 0 and say the dot product or scalar product, okay? Now notice those are vectors. You see that little arrow over there? Those are still vectors, but work is scalar. Please remember it's a scalar quantity. And remember, when you see negative work, that doesn't mean that it's necessarily going backwards. It doesn't mean it's going backwards. All right. We have positive work. What does that mean? That means work is being done on the object. In other words, how do I make that chair move? I got to do what kind of work on it? Positive work. I just did. What's the work that gravity's doing on those wheels? Positive or negative? Negative. And how do you know that, Mr. Shields? Well, is it going down in the floor when I push it? Is it going down in the floor like this new movie that's fixing to come out? What's this new Marvel's movie where they warp the buildings and do all that stuff? Yeah, Doctor Strange. Yeah, boy, it is strange, isn't it? The curvature of space, getting into Einstein stuff there, aren't they? They're warping all those buildings and everything. That's crazy. No, it didn't. So the work done by the gravity on those wheels, well, actually, since I pushed it horizontally, it'd actually be 0. But again, when we look at it, if it's on an inclined plane, however, it would be negative. Okay? All right, and we're going to look at an inclined plane problem like that too. Okay, and yes, friction does work too. Friction does work. Okay? All right, everybody good with the equations? Everybody good with the units? Okay? All right, now. Okay, that's just showing you how we apply an angle. And again, remember, it's the angle applied, okay? The applied force, okay? All right, now this is a good example. All right. Notice when the force is perpendicular to the direction of the displacement, the force does no work. So again, when it's perpendicular, like we just said, there's no work done. We've already went over that. The normal force, it would be 0. All right. If we move in the opposite direction, then work. Well, now this. Okay. Yeah, I see what they're saying. All right. If this were the case, then yes, it would be negative. Okay, we would have negative work. Okay, so it can mean a change in direction, but not always. Not always, but it can. Okay. All right. All right, weightlifter lifting weight. Notice the weightlifter does no work on a barbell as long as he holds it stationary. Okay? Remember, if there's no displacement, no work. You got to have displacement. When we start moving it, it becomes what? It becomes work. And yes, there would be work whether he's dropping or lowering because he's got displacement, okay? Now, all right, that's just saying that it's the same, displacement's the same, it'd be the same. Okay, let's move on. Let's move on. All right, now let's look at total work. Now, please understand that total work can also be written as work net. Okay? Work net. So, can you do work and not have any net work?
Yes.
Sure. What if you're doing work on an object, okay, but then you add in the frictional work, and the frictional work is equal to the work that you're doing. What's your net work? 0. Now, it doesn't mean you're not doing work. It just means there's no net work. Okay? And you can have situations like that, okay, where there's no network, okay? So just because you have a 0 network does not mean there's no work. So please understand that, because we're talking about the total work. And how do we define total? Well, we do total work or net by doing what? Work 1 plus work 2 plus work 3, whatever the works are. Work of gravity, work of normal force, work of friction, work of done by internal energy, which would be E. We'll get into that next semester. Okay? All right. You add them up, and of course, if some of these are negative, of course, you subtract it out. All right, now let's look at kinetic energy. Okay, what page are we on? All right, page 177, kinetic energy. Okay, and we've already talked about this a little bit. Energy of motion. There's another equation. There's it annotates it for you. We can write it K, KE. Typically, I try to always write it K. I used to write it KE years ago, kinetic energy, and PE, potential energy, or U. The only problem is you get over into electric potential, it gets into the same thing, and we get confused sometimes between electric potential and electric potential energy. And there's a difference. Electric potential and electric potential energy is not really the same thing, because electric potential is voltage. Of course, we typically write it V, but those words are similar, and we get confused, so we have to be careful. All right, so we write it K, 1/2 mv squared, and we can see how this is derived on page 178, and again, I'm not going to get into the derivation. You can take Newton's second law and expound on the acceleration part of it, go to your kinematic, go to the kinematic, this kinematic right here, change the x to s, okay, solve for acceleration and substitute in, and you can get that equation right there. Or you can do an integration and get it too. Okay. You can also get it by integration. All right.
Change the X to
S, yeah. All right. Because what happens is it becomes Fs is equal to 1/2 mv squared final minus 1/2 mv squared initial. And what is F times S? Work. F times S is work. And work is equal to kinetic energy. You with me? Again, solve for acceleration Change that to S. Okay? You don't have to. You can leave it X if you want to. And it becomes that, and that is work. And work is kinetic energy. Okay? And actually that equation there is the change in kinetic energy, delta K. Okay. All right. You with me? Now. All right. And again, look at here. Same unit. Work, kinetic energy, potential energy, all same units. Okay, now let's move on. Any questions? Again, doesn't depend on the direction of motion. All right. All right. Yeah. Ooh, I'm glad I saw that slide. All right. Let's look at that equation again. Okay, y'all. What happens if I keep velocity constant and I double the mass? What happens to kinetic energy? Doubles, right? Okay. What happens if I 2 times the velocity? I double the velocity, what happens to kinetic energy? Quadruples. That's another one of those little conceptual tidbits that you need to stick in the back of your mind or the front of your mind or the side or wherever. On a formula sheet. Because look, now let's think about it. So in other words, what's the best way to increase kinetic energy? By increasing mass or velocity? Velocity. All right, now let's think about car crashes. You ever seen a car wreck? Somebody doing 30 miles an hour. Oh, excuse me. Someone doing 20 miles an hour as opposed to 40 miles an hour. Man, there's a big difference in the car crash, isn't there? You look at a car at 20 miles an hour, there's not much done. You look at one at 40 miles an hour, pretty messed up. Well, why? Because the energy has been quadrupled. Now let's go from 40 to 80. Think about it. You've probably seen car crashes. This car was at 80 miles an hour. It looks like a tin can's been stomped on, right? You go from 40 to 80, it's been quadrupled. The amount of energy is quadrupled. So think about it. That's why speeding is very dangerous. Okay? Okay. Because when you double that velocity, you quadruple the energy. Okay? All right. You know, think about ballistics. Think about bullets, ballistics. You know, can a .22 bullet be just as dangerous as a .30-06 bullet? Well, a .30-06 bullet moves about twice the velocity of a .22 bullet, but it's also a lot more massive too. So you've got to take that into consideration. You know, a 22 bullets, what, 1.5 grams? Okay. Now, if you can make that, let me take that back though. Most 22 caliber bullets move at what? No, they move faster than a .30-06 bullet. I take that back. They move faster than a .30-06 bullet. So if the .30-06 bullet's moving at, say, 800 meters per second, and no, I'm thinking feet per second. 22 caliber moves at what, about 1,250 feet per second? Yeah, which would be about 400 meters per second. So yeah, .30-06 is about double that. Yeah, that's right. So you think about it. You're not only increasing mass with a .30-06, but you're also increasing velocity. So it's no wonder it'll put a hole in you like this when it comes out the other side. You know, 22 is going to do what? Go in and bounce around. Now, the bouncing around, it goes in, it'll reflect off, bounce off of bones and stuff. So yeah, they can be more destructive because they will, you know, ricochet off a bone in your body and they'll stay inside the body. But as far as damage, hole when it comes out the other side, you know, if you're shooting a hollow point, you're shooting at a deer, you want something that's going to, 22 is not going to knock a deer down. You know, he's going to stand up and go and run off, you know. You know, 30-06 bullet, he's down if you hit him in the right spot, you know. Okay? Especially if you hit him with a hollow point, he's going to have a big old hole. He'll probably blow his leg off on that side. Okay. Yeah. You deer hunters. Okay. Of course, most time you shoot what? Solids. 220 grain boat tail would do a lot of damage. All right. You with me? All right. All right, in there, that's what we're talking about. 4 times the speed. That's just going into the conceptual. All right, now, what about, here we go, another equation. Throwing a lot of equations at you today. Not too many. Please write this down exactly like you said. Work energy, this is called the kinetic energy work, a work energy or kinetic energy work theorem. You can write it both ways. Work kinetic energy theorem, okay, meaning what? I have no idea, Mr. Shields. Oh, baloney. That the total work or the net work is equal to the delta K. Everybody knows that delta is change in, and how do you get change in? You final minus initial. So, if my car is slowing, the total work will be what? If I'm moving along at 20 meters per second and I slow to 10 meters per second, my total work will be what? Positive or negative? Very good, negative. Because if this is 10 meters per second and this initially was 20 meters per second, don't matter about mass, 10 minus 20 is what? Negative 10, isn't it? We're forgetting the masses right now. So my total work was what? Negative. And my change in kinetic energy is what? Negative. And what does that tell me? If I get a negative kinetic energy, if I do the change in kinetic energy, it's negative. That means my object was doing what? Slowing down. Very good. So if delta K is negative, dadgummit, that means it's slowing. All right? If delta K is positive, that means it's increasing speed or speeding up. All right? My initial velocity was 5 meters per second and we increased it to 25 meters per second. What was the change in kinetic energy? Well, this. That means I increased in velocity or speed. Okay? All right. You see what we're talking about now. Okay? Okay, skater 0, skaters and kinetic energy changes nonetheless. Okay, so and here we're talking about pushing on a wall. There's no external force, external acting on the skater 0. The skater's kinetic energy changes nonetheless, right? Okay? So if you're not moving, no kinetic energy, right? All right. Okay, varying forces. I do want to get to this. What about now with constant forces? Now please remember, let's go over this again. Constant force. Work is equal to what? Force times S cosine theta. That's a constant force. Varying force though, guess what? Well, if we were to graph it, and I'm trying to think, will we do one with this? We may do a video analysis. I think I will do a video analysis with this because I got a good one that explains this, where we actually look at the integral of a non-constant force or a varying force. We get this type of slope. Notice that it's not a straight line. So therefore, how do we find the work done? We have to integrate all of that area. Okay? So then it becomes what? Well, you can do it that way, or we do it that way. Okay? We could break it up into little rectangles, but that's too much trouble. All right? So we do what? Work then becomes what? Now here they did put our x in there, didn't they? The x component of the force. So work done on a particle is the integral of the, it's actually the what? we're actually integrating the displacement. Force then is actually what? We kind of pull force out, don't we? It's a function of the position. So we're actually looking at what? The changing position, right? All right. So we integrate the force, a non-constant force, a varying force, with respect to what? Dx or x. Yeah. Mm-hmm. And again, like we said a minute ago, we're doing what? All this right here. All right? We're integrating the area under the curve. Now, y'all, let's see. What, was it Boyle's Law Lab? Did y'all do the Boyle's Law Lab where you looked at a PV diagram? Do y'all remember? Did y'all do that with Dr. Mishra? The Boyle's Law Lab where you use the syringes and the pressure gauges is a veneer lab. Did y'all ever do that one? And you had a PV diagram? Okay. Oh yeah, that's right. I forgot about that. Well, that is a good lab because that ties into work. Because a pressure volume diagram is work. And we'll look at that next semester. When we look at the change in pressure, the relationship of pressure to volume, it takes work. So a PV diagram is actually a work diagram. And we do the same thing there. We can integrate the area under the curve of a pressure volume diagram. I was hoping y'all did that. Man, that's a good one to do. Okay. That probably is the extent, that we're going to be able to. Oh, yeah. I do not want to get into Hooke's Law yet. Okay. If you want to be looking at some problems, I'll go ahead and give you 2 or 3 here. Oh, shoot. Dadgummit. Hang on. All right, numbers 1. Let's see. 1, 2, 3. Yeah. Page 194 and 195. We're going to do 1, 2, 3, 5, 8, and 11 so far. I've still got some more I want to work on, okay? So you can go ahead and be looking ahead at those. Number 11 is a really good problem. Number 5, too, because we're looking at the direction of the applied force. And that cosine of that angle really comes into play there. Okay?
Are we supposed to turn something?
Yeah, turn your chapter 4 and 5 worksheet in.
You want our chapter 5 problems?
No, just the 4-5 worksheet, yeah. I'm going to grade that one.